Good morning, students.
Morning, ma'am.
Good afternoon,
Good
ma'am.
afternoon, ma'am.
Good afternoon. So, can you see the screen?
Yes, ma'am.
Yes, ma'am.
Yes, so in previous lecture, we have seen Lyapunov function. Just recall it. What is a Lyapunov function? Let V be a fixed point of f, a real valued continuous function, capital VU, defined for all u in Rn is called a Lyapunov function for that f. And at V, provided that capital V at small v is equal to 0 and v at u is strictly greater than 0 for u not equal to v, right? And there is a ball b about v so that it satisfies this condition. Delta t vu is this function v at fu minus vu is less than equal to 0 for all u belongs to b. So if my function satisfies this properties, then we will call it as a Lyapunov function. And if this inequality here, this less than or equal to 0, if it is strict inequality, if it is strictly less than 0 for all u in B, then we say that it is a strict Lyapunov function. Is it? And we have seen some theorems and corollaries, and we have solved some examples based on Lyapunov function. So using Lyapunov function, we have established the stability of that this system u at t plus 1 is equal to a u of t, where a is my matrix cos of theta, sin theta, minus sin theta, cos theta, right? So here we have constructed a Lyapunov function v at u1 u2 because it is r on r2, v is defined on r2, we have constructed as u1 square plus u2 square, and we have proved that at origin it is equal to 0. We can easily check that v at u1 u2 is strictly greater than 0 at whenever u1 u2 are non-zero, right? And then we have found out that delta t v at u, which is less than or we got it as equal to 0, means we can say that it follows less than or equal to 0. So we can say that v is a Lyapunov function at origin, and then by that theorem 4.18 we can say that origin is stable. So this origin is stable. For this example we have shown using eigenvalues also. So this is another method Lyapunov function method to show that origin is stable. And also second example, in second example also we have established the stability of origin using this same Lyapunov function. Okay, so now today we will start fundamental matrices and Floquet theory. Let me type this. Fundamental matrices and Floquet theory. This is section 4.4. This lecture is 40.
46.
असं एक लेक्चर आहे ना त्याची लिंक 4.4. It is 4.4. Okay, so till now we have seen we have solved the system like this one, like u at t plus 1 is equal to a u of t, where a is a constant matrix. Like now we have to see, we have to consider the system. Okay, consider the system non-homogeneous system u at t plus 1 is equal to a of t u of t plus f of t. So number 4.15 to this, which is a non-homogeneous system if ft is not equal to 0, and if t is equal to 0, this is a homogeneous system. So, and its corresponding homogeneous system what will be its corresponding homogeneous system? U at t plus 1 is equal to a of t u of t. Already we have solved examples based on this. Okay, u at t plus 1 is equal to a u of t, like that. Now we have to see here if my matrix is with variable coefficients like a of t. So where we will give this number 4.16, where the matrix particular matrix, no, matrix function a of t will be assumed to be non-singular What is mean by non-singular?
Determinant.
For all integers t. What is determinant is? Determinant of that matrix is non-zero for all integers
Non-zero.
t. Then we will say that it is a non-singular matrix. So with this assumption, initial value problem for 4.15 must have a unique solution defined on the set of all integers. So we will be especially interested in the system where a of t is periodic. So when a of t is periodic, we will call that system as a Floquet system. But before going to Floquet system, let us know what is fundamental matrices and its properties, and then we will go to that Floquet system definition. Okay. So before going to that, we will define fundamental matrices first. Yes, let its matrix analog we will write first. The matrix analog of equation 4.16 can be written as or it is a here it is small. Now I am writing its matrix analog, so I am using here capital U. U at t plus 1 is equal to A of t. A of t is any matrix and capital U of t. So matrix analog we will denote by 4.17, where capital U of t is an n by n matrix function. Note that the solution of equation 4.17, note that the solution ut, note that the function ut is the solution function capital ut is the solution of equation 4.17 if and only if each of its column vectors is a solution of equation 4.16. 4.16, this one, homogeneous 4.16. Is it okay? This is just u at t plus this 4.16 is vector form, and this 4.17 is its matrix analog. So if capital U of t is a solution of 4.17, this matrix analog equation system, then each column vector will be solution of this 4.16. That is if and only if, means if a column vector is a solution of 4.16, then that matrix U of t, whose column is that vector, is also solution of this matrix analog U at t plus 1 is equal to this what we have denoted by 4.17. Okay, so first we will consider one theorem. If capital phi of t is a solution of equation 4.17, then either phi of t is non-zero for all t, or determinant of phi of t is equal to 0. Determinant here, either determinant of phi of t is non-zero for all t, or determinant of phi t is equal to 0 for all integers t. So what is this phi t? What is my 4.17? It is a matrix analog of the system 4.16. Okay, so what we are saying, if phi t is a solution of equation 4.17 matrix analog, then either determinant must be non-zero for all t, or determinant is equal to 0 for all t. So how we can prove this? So equation 4.17 means that is u at t plus 1 is equal to a of t u of t. Then either determinant, okay. So consider the equation, the matrix equation 4.17 given by what is u at t plus 1 is equal to a of t capital U of t. This is capital. If this is capital, this is also capital, not small. Okay. And what is given here? Phi t is a solution. Since phi t is a solution of above equation, above system, we must have what we must have. If phi t is solution means phi t will satisfy this equation, right? When we say that something is a solution of that system, if it satisfies, then we must have
Yes.
for all integers t, for all integers t, what we must have? Capital phi of, instead of u, phi of t plus 1 is equal to a of t phi of t, right? Now these are all matrices, so I can take determinant of phi of t plus 1 is equal to determinant of a of t into phi of t. So what is determinant of a into b? Property determinant of a into determinant of b, right? By properties of determinant. So I can write this as determinant of a of t into determinant of phi of t. That is for all integers t. Integers t. So, and what is the determinant of a of t is given? It is non-zero by our definition, where you can see here 4.17. What is given here? Ut is a n by n matrix function, and where is that? A of t.
A of t is non-singular.
Here a of t will be assumed. Here a of t will be assumed to be non-singular for all integers t. So here we can write where determinant of a of t is non-zero for all t. That is by our assumption, whatever system we are considering. So since now this is non-zero, so this is non-zero. Now if determinant of phi of t plus 1 is 0, then this is also 0. If left hand side is 0, right hand side must be 0, right? Are you getting this? This is what determinant of phi of t plus 1, and this is what determinant of phi of t. Now this is given to be non-zero. So our LHS is 0 or not. How it will depend? So either we will have determinant phi t is non-zero or determinant of phi t is equal to 0. Is it? There will be only two cases.
Yes, ma'am.
Because this is given to be non-zero. So since determinant of a of t is non-zero for all integers t, we must have either determinant of phi t is equal to 0 for all integers t, or determinant of phi t is non-zero for all integers t. If this was if this was 0, then 0 only we can say, we cannot say non-zero, but here it is given to be non-zero, so we will have both cases, either non-zero or 0 for all integers t. So which proves the theorem. So now we define fundamental matrix. Definition. When we call that phi t as a fundamental matrix, we say that phi t is a fundamental matrix, is a fundamental matrix of equation 4.16, provided that phi t is a solution of equation 4.17. Such that phi t is non-zero for all integers t. Determinant. So if determinant if determinant of phi t is non-zero for all integers t, then we say that our solution phi t is fundamental matrix for the equation 4.16. Okay, where what is phi t? Phi t is a solution of matrix analog whose determinant is non-zero. Okay, so instead of 4.16 and 4.17, we can write equation also. Let me write equation. U at t plus 1 is equal to a of t u of t. And here capital matrix analog. Capital U at t plus 1 is equal to a of t capital U of t. Okay, this is my equation 4.16 and this is equation 4.17. So we will have phi t as a solution, then we will have both cases, like either phi t is non-zero or determinant of phi t is non-zero, or determinant of phi t is equal to 0. So if determinant of phi t is non-zero for all integers t, matrix we will call as fundamental matrix for the equation 4.16. For example, if determinant of A is non-zero, then phi t is equal to A raised to t is a fundamental matrix. For the linear system with constant coefficients, what is that system? We have already seen u at t plus 1 is equal to a times u at t. A is constant matrix of with constant coefficients. Okay, we have already solved this such types of linear systems. U at t plus 1 is equal to a u of t. What is its solution? We know that its solution is a raised to t. So now if determinant of a is not equal to 0, then this phi t solution is called as fundamental matrix for this system. Is that okay?
Yes, ma'am.
Yes, ma'am. Particular example, we have already solved such linear systems in previous section. Okay, and we have shown a raised to t is a solution. Now if its determinant of a is non-zero, then we say that phi t is equal to a raised to t. That solution is a fundamental matrix. Now, so what can we say about note that remark or fundamental matrices for any non-singular matrix U0 non-singular matrix capital U0, the solution ut of equation 4.17 with u at t0 is equal to u0 is a fundamental matrix. Matrix of equation 4.16, and so there will be always infinitely many fundamental solutions. So always infinitely many fundamental solutions. How we can say there are infinitely many fundamental solutions? Because we know that if phi t is a solution, c times phi t is also a solution for that system.
Yes,
right?
ma'am.
Yes, ma'am. So c is arbitrary constant, so there will be infinitely many solutions, and if determinant of ut is non-zero means c times determinant of ut is also non-zero, where we are taking c non-zero. So determinant of that c times ut is also non-zero. Therefore, if there exists one fundamental matrix means there are always infinitely many fundamental solutions, fundamental matrices we can say. Okay, we can we can prove that theorem. Just as a consequence, theorem 4.10. If phi t is a fundamental matrix for equation u at t plus 1 is equal to a of t u of t, then psi t is another fundamental matrix if and only if there exist a non-singular matrix C such that psi t is equal to that C times phi of t. That is for all integers t. What is this theorem? If phi t is a fundamental matrix, so phi t is given to be fundamental matrix means its determinant is non-zero for all t, right? By our definition of fundamental matrix. Now, what we are saying, psi t is another fundamental matrix, so we have to prove determinant of psi t is also non-zero for all integers t, and it is a solution of that equation 4.17, which is a matrix analog of this equation 4.16. Is it? This is 4.16. We are saying capital phi t is a fundamental matrix that is given. Phi t is a fundamental matrix means determinant of phi t must be it is a solution of matrix analog, and determinant of phi t is non-zero for all t, right? By definition of fundamental matrix. Now what we have to prove? Psi t is another fundamental matrix if there exists a non-singular matrix C such that psi t is equal to C times phi t for all integers t. So one way is very easy. Which one is? Let psi t is equal to C times phi of t, where phi t is a fundamental matrix of equation 4.16. 4.16 means u at t plus 1 is equal to a of t u of t. And how C is given to be? C is a non-singular matrix. C is a non-singular matrix. So what can I say about determinant of C? What can I say about determinant of C? That is also non-zero. So then psi t is non-singular. Phi t is fundamental matrix, therefore, and C is non-singular matrix. So this implies determinant of phi t is also non-zero for all integers t. So this implies determinant of psi t is equal to determinant of C into determinant of phi t, so which is non-zero for all integers, right? Because determinant of C is also non-zero and determinant of phi t is also non-zero for all integers t. So what this implies? Determinant of psi t is non-zero for all integers t, right? And now what is remaining to show? When I can say psi t is a fundamental matrix if it is a solution, right? If it is a solution of matrix analog of this equation, right?
Yes, ma'am.
So also what is psi at t plus 1? What is psi at t plus 1? C times phi at t plus 1. psi t is c times phi t. So psi t plus 1 will be, right? But what is phi t plus 1? It is phi t plus phi is a solution of that equation. Which equation? U at t plus 1 is equal to a of t, u of t. So phi at t plus 1 I can write as
A of
phi
t
t
into
into
phi of
okay, u of t. Sorry, a of t. A of t into phi of. We can give here because phi t is a solution of equation 4.17, that is u at t plus 1 is equal to a of t u of t, equation 4.17. So phi t must satisfy this equation. So this implies phi at t plus 1 is nothing but a of t into phi of t. Is that right? C time, and what is c times phi t now? It is my psi t. So psi of t into a of t.
A of
So
t.
what this implies? Psi t is also solution. Also solution of equation 4.17. U at t plus 1 is equal to a of t u of t. So psi t is non-singular as well as it is a solution of matrix analog of 4.16. So by definition of fundamental matrix, we can say that therefore by definition of fundamental matrix, psi t is also a fundamental matrix for equation, which equation? 4.16. What is my 4.16? Small u at t plus 1 is equal to a of
A
t
of t.
u of t. Is that okay? So one part we have proved, if psi t is equal to c times phi of t, and if phi t is a fundamental matrix, then c times phi t in psi t is also fundamental matrix. Now we want to prove if psi t is another fundamental matrix, then psi t can be written as c times phi t, where c is, because we have to prove it is if and only if, right? Now conversely, assume that phi t and psi t are fundamental matrices of equation 4.16. So what can I say? I want to show that psi t is equal to c times phi t, where c is a non-singular matrix. So how I can say it? For some integer t0, let define capital C is equal to phi inverse of t0 psi of t0. This is C. phi inverse of T0 psi at T0. Then what can I say? Then psi T and phi T are both solutions. They are fundamental matrices. Both are fundamental matrices. Therefore, they both will satisfy 4.17. Okay, so the psi T and phi T are both solutions of which equation? Of equation 4.17 matrix analog, and satisfying same initial condition, right? What we are assuming here, phi T and psi T are fundamental matrices. Fundamental matrices means their determinant are non-zero and they are solutions of 4.17. So psi T and phi T both are solutions of equation 4.17, and since they satisfy the same initial condition. We are considering now for some integer T0, say C is equal to phi inverse of T0 into psi of T0. Then by uniqueness, if both are solutions of this of same equation with same initial condition, so what can I say? Phi T must be equal to psi T because there exists a unique solution, right? So by uniqueness, what is psi T? Psi T must be equal to C times phi T, right? From this for all T. Is that okay? Initial value
Yes, ma'am.
problem.
Yes, ma'am.
Initial value problem. If they satisfy same initial condition, means they must be same uniqueness. If they solution satisfy different initial condition, they may be different. But when we are saying for some integer T, this phi inverse of T0, we are saying C is equal to phi inverse of T0 psi at T0. So phi T and psi T will be both will be solutions of matrix analog with same initial condition. Therefore, psi T must be equal to C times phi T. So we can write its particular case as theorem 4.11. If phi T is a fundamental solution of equation 4.16, the general solution of equation 4.16 is given by psi T is equal to phi T times or C times phi T. Here C is a arbitrary constant column vector. So this proof of this theorem follows from here only. If phi t is a solution fundamental matrix, then psi t will be a fundamental matrix such that psi t is equal to C times phi t, where C is a non-singular matrix. Now this is a if phi t is a fundamental solution of equation 4.16, then its general solution will be C times. It must be C times phi t, where C is an arbitrary constant column vector. Is that okay? Are you there?
Yes, ma'am.
Yes. So for today, this much is enough. Tomorrow we will see variation of parameter formula for that for the equation for that system 4.15 non-homogeneous. This is for homogeneous now. Whatever we have seen for homogeneous. Now tomorrow we will see variation formula for this 4.15 non-homogeneous. What is the solution for the 4.15 non-homogeneous system? So we will stop here. Let me download the attendance. Okay, now you can leave the lecture. Tomorrow again we will meet at the same time.